Okay, I forgot to turn it on. Please remind me of to record the sessions. All right, so.
All right, sir.
All right, so this is the main idea. Okay, any of you have ever played with a dart? Play dart? Dart. D-A-R-T.
No, I haven't.
But you know what dart is, right?
Yeah, I think so.
Yeah,
you shoot something at an area, I think.
Yeah. So a dart is something that you throw to the bullseye, right? And you try to throw to hit the middle. Right? Okay. Okay. So what is the probability of hitting the center? Of hitting center of the bullseye. Right, so just guess, what's the probability?
I think it's 1 out of 10.
All right, so slightly too optimistic. Anyone else?
5%.
5%. Well, 5% is 1/20th. Well, it's much too optimistic.
0.
Yes, that is a better.
1 in 100.
0 is better approximations. I would say never. Why is never? Well, you can cheat a bit. I mean, cheating in terms of if you think you hit the bullseye here, you can take a microscope and see is actually missed by some distance. All right. If it's actually getting closer, you can take a better microscope, which zooms. It has more zoom, and see that actually you don't hit the bullseye. Okay, so that's why I say you'll never get never hit really the bullseye. Okay. Okay, that's the reason why you don't hit the center, but actually just a range of the center. But if the question hit the center, then the probability is basically 0. Okay. Okay, so that's what the idea is that you cannot hit the exact thing. Okay, yeah. So what we have is only approximate. it's only approximations. We never get hit of the real thing. And okay, so this is the main idea, approximations. Later, I'll tell you about something else later. All right, for example, you have a triangle. In geometry. All right, so this is a right triangle, and with the sides 1, 1, and all right. Even in the Babylonian time, people know the length of this one. So this Babylonia is a, let's see, maybe about 3,000. Oh, let's say maybe 500 to 700 BC. People know the length of this. The number R such that R square is 1 plus 1 equals 2. Well, what is this actually? Recognize the formula?
Pythagoras.
Pythagorean. Okay, they know already that the R cannot be a rational functions. So even people build R cannot be a rational function. Oh, sorry, rational number. Okay, so how they know that it is not rational? Well, let's see this one. I will use this rational, but we will learn it in more formal way. Okay, so they suppose R is rational. Okay, so what does mean? R is a rational number. So R is a ratio where A and B are both integers. All right. So this is what you call a rational number. All right, so let's square it. You square. Okay, so what we have is R square equals A square over B square. Okay, and that's equals to 2, right? Because of this. Okay, so let's rewrite. What we write is this one. So A square is twice of B square, meaning that twice meaning that A square must be an even number. Okay. So the question is, what about A? Can A be odd number? Well, the thing is, A cannot be odd number because odd number, if you square an odd number, it must be odd. Right? So that means A must be. Says if A is odd, then a square is also odd. Okay, so this is the idea, even number. So what is this even? Then what is even number? Even number is a multiple of 2, right? So then we write a is 2, say c, for some integer c. Okay, then we substitute this to the square. Let me just this star and 2 star. Okay, so what you have, this is 2c square root, so 4c square is 2b squared. Okay, so simplify, that means, so c squared, oh, sorry, right? With the same argument, we see we have b is even. B is even, meaning that, so b is 2d for some integer d. Oh, what's wrong with this one? I forgot to mention something like this. Here. This one. R is rational number, so R is A over B. But we impose something, some conditions. For integer, simplest form. What do you mean simplest form? Let's see. I'll give you an example. What is not simple? 2 over 4 is not simplest form. Why? Because 2 over 4 can be simplified to 1/2. Okay, so 3/9. 3/9 is not the simplest, because if you simplify, it's give you 1/3. Okay, so that's what I mean the simplest form. A and B don't have a common denominator. Okay, don't have common denominator. Other than 1. Okay, all right, so that's meaning the simplest. We assume the simplest. All right, but when you have this, A is 2C and B 2D. So what we have so far, so R is A over B, A is 2C, B is 2D, so this is C over D. All right, so that means C over D is simpler than A over B. A over B is not the simplest. Okay, so it contradicts our with what we suppose here, simplest, which contradict what we assumed in the beginning. All right. what does it mean if it contradicts? Those contradictions. That means that the R cannot be rational number. Okay, so this is what we call a irrational number. Okay. What is irrational number? Well, irrational number is something that has no, the decimal expansion of rational number has no pattern whatsoever. Okay, rational number. Decimal expansion of irrational number is of infinite length and no patterns whatsoever. Okay. And what does this mean? Well, infinite length, meaning that you can never write down the exact value. Can never be able to write the exact value. Okay, only approximations. Okay, so other thing is just the number that you know, pi. Okay, so if you check your in BBC or CNN recently, last week or so, it says there is some expert has found the 32 trillion expansion of the number pi. So this is the record using a supercomputer to work it out in, well, how many? 20 days or so, okay, to work out this 20 trillion means it to the 10 to the, what's the number? 10 to the 12, right? So record in 2021, 12 times expansion, digit expansion. Okay. And in fact, you can download an app named the SuperPi to test out your smartphone processor. Your smartphone processor can compute, for example, 4 million expansion of pi in less than 1 minute. Say, it's one way to benchmark the strength of the processor. Okay. All right. So with this idea of approximations, so if you have a exact value, we hope that this is approximations, right? If you change this to equal sign, Okay, not this weakly equal, meaning that approximately. This weekly. So you have approximate value plus the error. Okay. Now the thing is how to deal with error, because if you deal with error, sometimes error getting bigger and bigger, and that's the process give you some messy stuff. Okay. So basically, in calculus, back to calculus, think about CISO. Okay. But now you have a process, but now you have x plus error. Error in terms of x. Okay, all right. And you have the output would be y plus some error. Okay. But you want to have some process which is quite good, meaning the error is so because we cannot you cannot have a precise value, then error must be there. You cannot avoid this. And so the output with value with error is so unavoidable. Okay, but the thing is how to make sure that the error uh, still what you reasonable error. So how to deal with system? I would say CISO with reasonable error. Okay. So this is why we need calculus. Okay, so the answer calculus is computing this kind of CISO with error. So the calculus we do the approximate. So what does mean reasonable? The thing is we can control the error. Okay. Example. And so example. I guess this is the last thing. Then I will stop here, and how to compute it. We postpone it later. Okay, so this is the system. Build a water tank with volume okay, build water tank with certain volume. Oh, just build water tank. Spherical. Okay, so here is the volume tank. With certain volume. This is the material. And the thing is what you measure is the radius. Right. Okay. So in formula, how we describe this in formula? Is volume. Okay. For example, we would like to have say later on pi meter. Okay. Plus minus some error. Say percent. Okay, so the thing here, you have material is R, the radius, plus some, this is the error. Okay, so the question is, now not build, but compute. Oh, because we know this is a spherical water tank, and V must be, we know that 4/3 R squared. Oh, sorry, R cube. Volume, a spherical volume. Just, okay, that's easy. Okay, so you want to have water tank of this volume, certain volume, with certain error, and then you have to approximate the radius. Okay, so objective, build spherical water tank with volumes of pi plus minus right, or just say 1%, doesn't matter, right? So this is the error. Now the thing is approximate R, meaning that what is error? Okay, so that's basically calculus questions. We'll do this next time. Okay, so why we need differential integrals? Okay, we'll see that things. Okay, another story is that again system X and Y. Okay, so the thing is vary the value for Y. Oh, sorry, for X. Question is how the okay, so this is basically the question about differential, meaning if the f prime we know that is positive, that means if x increasing, when you increase x, then y also increase. Okay, if x increases, then y decreases. Okay, you have this kind of system actually. And why we need integrals? Well, you sum you find the cumulative sum of the sum, sorry, because of x, then this is the integral. Okay, so this is a calculus that we want to learn in the next 2 semesters. Okay, so that's as a tool for to study system, basically. I am using approximations. So in the end, what I would like to say is that what is calculus? Well, the thing is I would say the art of computing of approximations. Art of changes. When something changes, then there are bound to be calculus there. Okay, so you want to quantify the changes. If you deal with commutative changes, then this is the integral. The changes itself, that's the differential. All right, so that is what we want to learn in calculus. So this is the main idea, what we want to learn. All right, questions?
Hello, sir.
Yeah.
When you said about the errors, how do we determine the errors?
There's quite a couple of tricks. We'll do that in example next time. We want to follow up this one. Well, suppose you're a contractor, right? So you get a contract, build this kind of value. The thing that you don't want to do is just cut material, try to build the water tank, and then miss the specifications, right? For example, well, that's too much, and then you have to rebuild. And then the second time, well, still miss the error. All right. So you don't want to do trial error. So you have to get the error here is quite right. The thing is how to approximate the error. So this is the question of the calculus. That's the reason why we need a lot of inequalities, actually, a few inequalities. But with the calculus, we can do this easier later on. But we'll do this from scratch.
Okay.
It's a bit technical, but we'll do this one. We'll show you how to do this. How to approximate error, because the thing is that we can only approximate error. There's the way you can compute the exact error. Let me write down. The thing is the error. You can say error is exact minus the approximate, right? Actual. You want to cut say a wood 1 meter long, 1 meter in length, right? Well, you cut it as much as possible, as good as possible. There's bound to be an error, right? So the actual thing, the exact is the ideal. The actual is, well, you miss by 1 millimeter or 0.1 millimeter, half millimeter, or whatever. That's the actual. The error is the difference. Okay. So the thing here is that there's no way you can get the exact error. Cannot be exact. The thing is, if error is exact, right, then sorry, I should write something like this. Sorry, let me write something like okay, so the actual thing, measurement, is the ideal plus error. Okay, so that's this thing. All right, so the thing is, if error is exact, then the actual measurement is exact. But this cannot be true. Okay, so that's why the error can only be approximated, but never be exact. So the idea is how to approximate error. That's calculus. Okay, so it's pretty much different from what you learn in calculus as a computing tools when you're in high school.
Okay, thank you, sir.
Okay, so we'll find more about calculus, how it's the things opens up. It's sort of a exciting as a way of thinking. So you're learning calculus here is not only as a tools of computing, but as a way of thinking, actually. Thinking in terms of calculus, in terms of approximations. So one way is you give up the exact values, the ideal values. There's no way you can get the ideal values. You have to just accept it. There are bound to be errors, but as long as the error is controllable, then it's actually okay. Okay, and in life you deal with error all the time, actually. Right, so calculus is everywhere. Okay, any questions? Okay, if not, then we'll stop our sessions here. Record. So stop.